So in this video, we're going to implement a min heap. Okay, and so what I've done here is just take care of setting up one of my file headers and that sort of thing so we can get going. So unlike other trees, we don't have to define a node type because we're using our vector as our underlying type. So let's begin. Oops, forgot my namespace. Let's begin by defining our class. Class heap. Okay, and we'll define some private data. Okay, and we will start with an internal variable. Let's do ints for now, called heap. Now, one of the reasons I put an underline in front of this is because that way I can distinguish which are member variables and which are local variables. It's just my personal style. Oh, I'm going to forget this because I always forget semicolons. All right, so now let's define some internal methods that are only used by our tree. I'm going to do this all in the header file because I just prefer it that way. So let's first define our write, which takes a parent. Okay. Similarly, we will define a left that also takes a parent. And finally, we'll define a parent, which this time will take a child. Okay. Now, as we said in the prior video, here, actually I want to put left on the top because left is the first one. And comment, left child. Node stored in the vector at position 2. So let's implement this guy here. We will say int let's define this as equals 2 times parent. Right? And then we're going to make sure we don't extend past the end of our heap if left is less than heap size. Return left. Oops. Okay. Otherwise, we're going to return -1, which we're going to use as a sentinel value to say things are not right. Now, for our write method, we're going to steal our comments here. And reuse them. Except change the details. Now, we're going to do the same thing here with the implementation. Just changing one little bit of it. Changing the names, of course. And again, we return a sentinel if there's a problem. Now for parent, this time we're going to kind of go the opposite direction, and we're going to say parent child node stored in the position of floor of. Okay, so now let's implement this guy, and we'll say int parent equals child divided by 2 if parent equals 0, because we're not going to use the 0 slot. We're going to return -1. Otherwise, we will return the parent. Okay. Notice that by using an int type here, we automatically implement the floor function because it truncates everything. So now let's define some public methods. First, we're going to initialize our heap with a constructor. And we're going to say push back. And we're going to give it -1, which we use as our sentinel value, so it fills in that first position. Okay. The next thing we're going to do is have an insert method. And it will take a value. And what it will do is push it on the back. And then what we'll do, we'll define a stub for it now. We will say void heapify upwards, and we'll take an initial value. We'll call it and put that here. We're just going to stop it up for now. Have a similar heapify down that we'll use as well. You know what? I don't like these names are too long, so we'll call this down and we'll call this up. Okay. So now in our implementations, all we got to do here is push back the value, and we're going to heapify up, and we will give it the size. Heap.size, -1. So basically we're going to start the heap at the node we just add. In fact, I want to change the name of this. It's not really initial. It should be last add. And this won't be last add. This will be, well, actually, flip it out. It will be, call this, let's try that. Well, let's just call it last instead of making things more confusing. Okay, so then we're going to heapify up to reassert our heap condition, right? And so now we'll also now have our other method, delete min. But first, let's comment our code a little bit here. Insert a new value into our heap while maintaining the heap property. Okay, now we're going to have another function, remove the minimum value heap while maintaining the heap property. And we will call this, it'll return an int, and we will call this delete min. Okay. And this guy, we're going to say if heap dot size equals 1, meaning there's only that empty spot in there, then what we'll do is we'll throw an exception, empty heap, what doesn't it like here? Oh, that's a visual screen. Let's just say we can just get rid of this right now. I don't really like that, but it'll do for now. All right, so then what we're going to do is we are going to say okay, so now while deleting it, we're going to now continue. And what we're going to do, because our first entry is a holder entry, we will say heap of 1, oops, can't type today, equals heap.at, heap.size, -1. Remember, we're 0 based. Okay, and this will copy the last item we just inserted, potentially, into the first item. And then what we'll do is get rid of that last item. All right. And then we will equify down at position 1. Right? So basically, now notice this deletes the first item and it doesn't necessarily return it. By the way, this is wrong. It should be void. It doesn't return it. We need the equivalent of a peak. Sorry about that. So here we go. Where's that? All right. So now we will have void extract min, which gets us the min value before we delete it, and here we say if heap size 1, return -1. Otherwise, because we now know it's always in the 0 position, we'll say heap sub 1. Well, I made a mistake here. We'll say int. All right. Now, to complete our ADT, we're going to add a couple other utility functions here. We will say size, and that'll just return heap size. And that's the size of the heap, not the number of elements in it. Okay. Which actually in this case would be the same. Sorry about that. Now we're going to also write a quick utility to print our heap. And what it will do is just run through here and for auto pause equals heap begin plus 1 because we don't want that -1. Pos doesn't equal heap end. And then, okay. And then all we're going to do here is count. And then finally here we will count. Right? Okay, so we've got everything done except the two functions that we really need. Heapify up and heapify down. So, and again, I'm going to change the name of this again. That's index is what it should really be, to be honest. Because you could heapify at any point. All right, so when we heapify up, let's take a look. Okay, so if our index is greater than or equal to 1, and the parent of our index is greater than or equal to 1, so we're not getting into that holding space in the beginner, and heap, so parent index is greater than heap subindex, remember, the parent must bubble to the top, then what we're going to do is do a swap. Okay, we will say int temp equals heap subindex, and then we will say heap index equals heap of the parent index, and then we will say heap of the parent index equals temp. This is just a standard variable swap like you do in a sort. And then what we're going to do is continue on up. But this time we're going to heapify up on the parent. Up on the parent. And this will give us what we expect because this each does work towards the loop because we keep heapifying, and then we will break out when the parent index is less than 1, or we don't have any inconsistency in our heap. When this is false and we don't have things out of order. Okay, so now we're going to go through and do the opposite, which is heapify down. Shoot, did I put that in the wrong thing? Yes, I confused the two. Sorry. Okay, heapify down. This is a little different. First, we're going to get the left child equals left of index, and then we'll say right child equals right of index, and then we say if left child greater than or equal to 1 and the heap left child is greater than heap the right child, then equals right child. This enables us to handle deleting a leaf when we heapify down. If left child is greater than 1 and heap index is greater than heap of the left child, then we've got to do our swap again, which I'm going to steal the code here, but we'll have to change some things. Now we're swapping for different reasons because we have to move things around a little bit. This time we heap index and left child and heaps left child equals 10, and then we're going to heapify up heapify down actually the left child. Now I would strongly suggest tracing through this code to understand what's going on. Now, if I did my job and we got through here with no errors, we can implement a very simple main program to test it, right? So, let's go over here, main, get rid of this, include heap h. Standard. Okay, so first we're going to create a heap, and then we will heap insert 5. Put a couple more inserts. Trying to make my life easier. Let's do 7. Let's do 1. Let's do 99. And just to really, let's do 0. Now, let's print out our heap to see what it looks like. And see our first priority. Extract them in. Our heap. Okay, now let's delete a couple. And let's do this by heap delete min. And then we'll repeat this after each one so we can see what's going on. Actually, this is backwards though. That won't work the way we think. Okay. Now, if my typing withstood the test of time, and we try running it, let's see if I get through it without any compile errors. Oh, I have a typo in heap here. Okay. So now, if we run it, let's see if we get any errors this time. Oh, okay, so we inserted in our main, we inserted 5719990 and when we put it out to priority, we got 0, which is appropriate. When we delete, we first get our priority to 0, and then we delete it, and notice it's no longer in here. And then when we delete the next one, which is a 5, notice it, because it's rejuggled our heap, it deletes the 5. So there you go. That's the basic implementation of a heap. Walk through this code and get comfortable with it.